The use of living microbes to treat contaminated sites is known as bioremediation. Bacteria, fungi, algae, and other microorganisms are used here. Scientists have successfully developed various bioremediation approaches to remediate contaminated environments.
We can adapt two types of strategies here. In situ bioremediation refers to the use of decontamination procedures on site to clean polluted soil or groundwater with minimal damage to the soil structure. These bioremediation approaches are cost-effective because excavation processes are avoided. However, the cost of designing and installing complex equipment to increase biotic activity in bioremediation is a major worry. In situ bioremediation approaches have been employed to detoxify chlorinated solvents, dyes, nutrients, heavy metals, and organic waste sites. Bioventing, biosparging, and bioaugmentation are all included in situ bioremediation techniques.
Bioventing is a form of in situ bioremediation technology that encourages aerobic decomposition. By delivering oxygen into an unsaturated zone, it improves the innate capacity of indigenous microorganisms to break down organic pollutants adsorbed to soil. Through vertical and horizontal wells, air is injected directly into the contaminated zone. Only the amount of air needed for degradation is used in this procedure. It also reduces pollutant volatilization and discharge into the environment. In the 1990s, bioventing was one of the first large-scale technologies to be implemented, and it is now widely employed in commercial applications. Bioventing can be done in two ways, actively or passively. Biosparging is the process of pumping pressurized air or gas into a polluted area to stimulate in situ aerobic biological activity. This technology targets chemical substances such as mineral oils and benzene, toluene, ethylbenzene, xylene, and naphthalene (BTEXN) that can be biodegraded under aerobic conditions and are used to treat soluble and residual contaminants in the saturated zone. By giving oxygen to the microorganisms and increasing the interactions between air, water, and the aquifer, the injection of air and gaseous nutrients if needed promotes the development of the aerobic microbial population and thereby enhances the bioavailability of pollutants. The goal of a sparging system is to increase pollutant biodegradation while minimizing volatile and semi-volatile organic compound volatilization. Bioaugmentation is a type of in situ bioremediation. It involves researching the local indigenous varieties to see if biostimulation is viable. Bioaugmentation is the addition of extra archaea or bacterial cultures to boost pollutant breakdown, whereas biostimulation is the addition of nutritional supplements to boost bacterial metabolism.
There are four types: land farming, biopiles, bioreactors, composting.
Land farming. Land farming is the most basic method of bioremediation. Contaminated soils are blended with soil amendments like bulking agents and fertilizers before being tilled into the ground. They are excavated and spread out in layers of around 0.3 meters thickness on a lined treatment area in land farming. Periodic flipping of the bed and the addition of nutrients can help with bioremediation. Microbiological and oxidative mechanisms degrade, convert, and immobilize contaminants. Biopiles. A biopile is a type of ex situ treatment that uses biological processes to transform pollutants into low-toxic byproducts. It is often used to lower petroleum component concentrations in soils by utilizing the bioremediation process. Biopiles are a type of remediation system that is used for a short period of time. To maximize and manage the pace of biodegradation, excavated soil or silt is piled over an impermeable base or pad with aeration. Pads are often designed with a cover and sufficient drainage to manage precipitation exposure, as well as probes to monitor temperature, moisture content, and pollutant concentrations. Depending on the site's qualities and regulatory requirements, optional equipment may include a moisture addition system, leachate collection system, and off-gas treatment. Bioreactors. Any manufactured equipment or system that supports a biologically active environment is referred to as a bioreactor. The bioreactor approach is an ex situ biochemical processing system that utilizes microbes to remove contaminants from wastewater or pumped groundwater, as well as the solid and liquid slurry stages of contaminated soil treatment. This process might be aerobic or anaerobic in nature. Composting. The employment of a biological system of microorganisms in a mature, cured compost to adsorb or break down pollutants in water or soil is known as compost bioremediation. Aerated static pile composting. Compost is formed into heaps and aerated with blowers or vacuum pumps, and windrow composting. Compost is deposited in long piles, windrows, and occasionally mixed with mobility equipment are the two most frequent composting methods. Windrow composting is often thought to be the most cost-effective composting method, however it may also produce the greatest fugitive emissions. In bioremediation, compost is referred to as tailored or designed compost since it is prepared specifically to treat certain toxins at specified locations. Addition of bulking agents. Excavated contaminated soil is combined with bulking agents and organic amendments including wood chips, hay, manure, and vegetable, e.g., potato wastes. Consumption of contaminants. Contaminants in soils, ground and surface waters, and the air are consumed by microorganisms. Digestion of contaminants. Contaminants are digested, metabolized, and converted into humus and inert byproducts like carbon dioxide, water, and salts. Successful degradation. Many types of pollutants, including chlorinated and non-chlorinated hydrocarbons, wood-preserving chemicals, solvents, heavy metals, pesticides, petroleum products, and explosives, have been successfully degraded or altered using compost bioremediation. Genetic engineering approaches. Genetic engineering has widely been applied in bioremediation procedures recently. It involves the application of genetically engineered microorganisms on the contaminated sites for the management and remediation of these contaminants. The use of genetically altered organisms for bioremediation would be an environmentally viable and cost-effective option. Recombinant DNA and RNA technologies have been used to create various types of genetically engineered bacteria that have been used to remove heavy metals and hazardous compounds from contaminated locations. The effectiveness of bioremediation of contaminated places can be improved by a symbiotic connection between genetically altered bacteria and transgenic plants. This involves techniques such as phytoremediation and its types. Phytoremediation. Living plants are used in phytoremediation technologies to clean up soil, air, and water that have been contaminated with dangerous pollutants. It's defined as the employment of green plants and associated microbes, as well as appropriate soil amendments and agronomic techniques, to either contain, remove, or render harmful environmental toxins harmless. Many plants, including mustard, alpine pennycress, hemp, and pigweed, have demonstrated their ability to hyperaccumulate toxins at toxic waste sites. Phytoremediation has been used successfully to recover abandoned metal mine workings, sites where polychlorinated biphenyls were deposited during manufacturing, and mitigation of continuing coal mine discharges, decreasing pollutants in soils, water, and air. Metals, pesticides, solvents, explosives, and crude oil and its derivatives have all been reduced through phytoremediation operations around the world.
Advantages. Positive impact on the environment. The most significant advantage of adopting bioremediation technologies is the positive impact on the environment. Nature is used to fix nature in bioremediation. Safest and least invasive. This is the safest and least invasive soil and groundwater treatment available when properly done by skilled workers using specialized bioremediation equipment. Highly treatable. Organic pathogens, arsenic, fluoride, nitrate, volatile organic compounds, metals, and a variety of other pollutants such as ammonia and phosphates can all be treated by bioremediation. Removal of pesticides and herbicides. It works well to remove pesticides and herbicides from aquifers, as well as seawater intrusion. No risk of transportation. For the most part, work is done on site, avoiding the risks of transportation. Less requirement of equipment. Except for specific parts, very little equipment is required. Low maintenance cost. Maintenance costs are low, and input costs are low. Reduction of liability. Liability is reduced since toxins are less likely to escape. Low energy consumption. In comparison to incineration and landfilling, there is very little energy consumed. Disadvantages. Treats only biodegradable substances. The major shortcoming of bioremediation technology is that it can only deal with biodegradable substances. Hazardous new product. Researchers have also discovered that the new product created following biodegradation is sometimes more harmful to the environment than the original component. Time consumption. Finally, the procedure takes time, particularly ex situ bioremediation, which necessitates excavation and pumping. Conclusion. Bioremediation has now been frequently employed as a solution for pharmaceutical pollution. However, the lack of understanding of microbial processes at the polluted niche, the bioavailability of the pollutant, survival of non-native species, and the lack of an integrated multidisciplinary approach are the major hurdles in translating lab-scale research to the field. Thanks a lot for watching. Please subscribe the channel and support the effort. Meet you in the next video.